So I'd like to welcome everyone to this this session this afternoon. Let me bring this over here so we have some sort of background here. So we're going to have a session where we're going to talk about our Inspire software, where we're going to go through how to do structural analysis and optimization. This is going to allow you to create better vehicles, stronger vehicles, lighter vehicles, and to help you win competitions. I'm joined here by my colleague Darius Fadenelli, who's going to come on in just a moment and talk to you about our competition optimization and analysis competition that we're running here. But a bit about myself first. I am the technical account manager for Altair. I've worked for Altair for, oh my, coming up on what, 14, 15 years, something like that. I have been working in education entirely for the past 2 years with Darius, and it is our hope that we can show you and introduce you to the concepts of analysis and optimization, not only for what it's going to assist you in the competitions, but on the realization that the softwares like this and the analyses and the things that we're going to do and demonstrate to you can help you when you ultimately get a job. These are the tools that engineers are using, that companies are using to create more intelligent designs, to create stronger designs, and to create lighter designs. So I will spend probably about an hour and a half going through a demonstration of the software. And then we will have probably a good half an hour question and answer session at the end, where we'll be able to talk about any questions that you might have. Additionally, whether it is for what Darius is going to talk about right now or my session, there is a Q&A window, so please do not hesitate to post any questions that you might have in the Q&A. I will get to them at an appropriate time. We'll take a pause break every few minutes or every little bit to address any questions. But please, any questions that you have, put them in there. I'd be more than happy to address anything. But right now, what I'll do is I'll turn it over to my colleague here, Darius Fadenelli, who's going to talk to you about our simulation competition. Additionally, and not to be antisocial, but I am going to turn off my screen share or my camera here, just because it tends to stream better without it. So I'm going to stop my video. I'm going to stop sharing so Darius can share anything that do you have anything you need to share, Darius, or just leave this as background?
Nope, I won't share anything.
Okay, then I'll just leave this sharing. I'm just going to stop my video, and as soon as he's done, we'll get into the class.
All right, well, thank you, Eric, and thank you everyone for attending today's session. You'll be pleasantly surprised about what you're going to see today. Eric, first of all, is a fantastic instructor. He's, as you probably saw in his very, very short bio, he's taught thousands and upon thousands of students and commercial, employees, many of our products, and he is one of our, most requested trainers. So you'll definitely enjoy what he's going to cover today and how he covers it. So expect to be amazed. You're here today because of the interest in the challenge that we have, the Altair Simulation Challenge, and just even by reading the description of it, our goal is really to help promote simulation in all endeavors, in contests that students participate in. And we thought this would be a great way to help promote, the eFest and provide an opportunity for students to learn some great tools that are being used in industry right now by many top companies out there. If you name the top ones you want to work with, you'll find that most of them use our tools. And we hope this helps with that. That's the foundation of why we're doing this challenge, to really help the students get the jobs at companies like that. And partnering with ASME and having this challenge was a great way to do it. And we hope to expand upon this in the future. So, and again, the other thing is this is available for any of students who are registered for the Digital eFest. So you can promote it to your other student friends. That means you'll have more competition, but it'll allow them to participate in here. Again, senior design teams and so forth are, valid teams that can take part in this challenge. And the goal is that you can then figure out how to use simulation even better. Again, as anything in life, the more you utilize it or practice it, the better you'll be. And doing something like this that you can put on your resume is also a great material to to have on it. So that was the initial implication of why we're doing this challenge, and we wanted to make sure that we have trainings. So Eric's session is one of a few that we're offering. Then we're offering one for the lower energy consumption with optimized CFD. That will be happening later, and we also have our you know forum or community forum that you can go to ask for questions. And if you do sign up as a team, officially get a sponsorship through this to participate in this challenge and in eFest, you can email our technical support line. I mentioned you're participating in this challenge, so you would just email hwsupport@altair.com, and a technical specialist will then reply back to you to help you out with questions that you have. As Eric will probably show, there's a wealth of additional material out there. He's done a fantastic video series that he can point you to, and also the tutorials that we have. Once you see what Eric does today, I think those will just elevate you even further into understanding what you're are capable of doing. It's important to get us your primary report by March 8th. Again, depending on how many are submitted by that time, we might extend the deadline, but please do your best to get a preliminary report. Follow details that we have on the instructions for this competition, and then that will allow us to understand what you're doing and be prepared for when you give us the final report. So we hope you enjoy this challenge, and as Eric said, we'll be here to take questions and about the product or even about this challenge. So actually, if you have any questions right now, I don't know if we can take any questions, Brandy, from the audience.
We can. I don't see any in the Q&A yet.
Okay. Well, if you have one, right now, please feel free to put it in. Or if not, we can wait till when we ask other questions and go from there. But we do hope you enjoyed and truly, appreciate the power of some of the tools that you're having access to. So thank you and good luck, everyone.
Excellent. Thank you, Darius. I appreciate you taking the time to talk about that challenge. It is an exciting opportunity to become more familiar with our products and perhaps win something in the process. But with that said, let us move on to talking about the software. So the software that we're going to be addressing today is our Inspire software. Inspire was created a number of years ago to bring the capabilities of analysis and optimization to a broader audience. In the past, analysis had been a tool that, finite element analysis in particular, had been a tool that was reserved for the select few who had the background education in analysis, who had the training in school to learn about finite element theory, to learn about the ideas of what makes a good element, what makes a bad element, and then combine that with perhaps weeks of training in a software, meant that it was always just a select few who did finite element analysis, and it also tended to be used just as a validation tool. You'd come up with a design. When you got to the end of the design process, you'd send it off to an analyst to have them take a look at it and make sure you didn't make any mistakes. Where the reality of the situation is, the best place for analysis to be conducted is at the beginning, during the initial design stages. It allows you to make changes to your part for the better at a time when you have the most freedom to make changes to your design. And so to do that, we needed to make sure that we had the power and the accuracy of our enterprise level analysis softwares, but the ease of use and understanding of a CAD package. And that's where Inspire came about. This is the interface for Inspire. You can see it's very, very CAD-like. It has a very CAD-like look. And it's all geometry based. We don't see the embedded panels, the embedded functions, the confusing setup of a standard finite element analysis package. This is much easier to use. And we wanted to make it entirely geometry based so that we didn't have to deal with the fine tuning of meshes, allow our packages in the background to create a good high quality mesh for you while you focused on what was most important, and that was getting your product, your part ready for analysis, setting up things like loads and materials and constraints. My presentation is going to be almost entirely demonstration based, but there are a few slides that I want to show you, simply because I think they really put the concept of finite element analysis and what Inspire can do for you into context. So, I mean, we have this original slide, and I'll get this just so it's in the recording. But what is Inspire? I'm not going to read this whole thing to you, but it's going to allow you to produce designs faster, allow you to produce smarter designs and lighter designs. And the way that we're going to go about doing that is through this process here. And there are two main processes that you go through when you're utilizing a software like Inspire. And that is, you can either take a current design that you have and run it through the analysis, run it through the optimization to create a better, lighter design. Or ideally, you'd actually invoke the use of Inspire before you even have a finalized design and allow it to be utilized in the actual design process. But what we're going to do is we're going to take some sort of initial design, whether it's a good finalized design or just kind of a broad strokes idea. And we're going to take that and run it through Inspire, which is going to provide you with an optimal layout of the material. So you can see here, this large bracket, it's a suspension bracket for a truck, and this thing is enormous. I've talked about and shown this slide for years until it was actually just in the past year or so that I actually got to hold one of these parts, physically hold it. And this part is huge. It is a beast. And it weighs a lot. And it's a great design. There's no doubt that this part is going to survive whatever scenarios it encounters. But at the same time, it's over-designed. And when you over-design parts, it means you're carrying around a substantial amount of weight, a substantial amount of mass, a substantial amount of material that you don't need. Your part is more expensive to produce. And it's going to decrease the overall economy of your vehicle because you're lugging around a bunch of steel or aluminum or whatever that you don't need. So the optimization is going to provide you an optimal material distribution from this large block of material here. What material is necessary, and only what material is necessary to achieve the goal that you're looking for. And you're going to get something that looks like this coming out of Inspire. Perhaps not quite the chromy look that was rendered in other softwares, but you'll get this shape. And from there, you can engineer a part that takes into account the advice that Inspire is providing you, the information it's providing you about material distribution, and end up with a beautifully engineered part that in this case is a 55% reduction in mass. And that's the sort of results we see out of Inspire. Maybe not everything is going to be a 55 or greater percent reduction in mass, but a 25, 30, 40% is very, very common. And I've seen 50, 60, even 70, 75% reduction in mass in numerous optimizations. And it's not because the original design was bad or improper. It's because the original design didn't take into account the simulation-driven concept that allows you to partner with an analysis code like this to help you understand a material distribution that's going to get you the fastest, lightest part. Another advantage that we get out of the material or the simulation-driven design is a reduction in design time. So this is a bracket. This bracket goes onto an A380 door. Excuse me, and it's going to allow that door to open up. There's some door hinge brackets. Actually, that's what we're going to be using in the demonstration here that are holding this to the frame and to the door. And using the conventional design process. What is the conventional design process? That means going through and coming up with a design, iterating that design out, and then going and taking that to a finite element analysis software to make sure that this design meets your specifications. And when it comes back, it either is going to let you know, no, it didn't meet your specification, then you're going to have to redesign it, or it's going to say yes, and it's perhaps even going to give you a factor of safety, and then you realize that maybe you over-designed your part. But either report back from FEA means you're going through the design process again to either fix problems or perhaps to take lightweight or take material out to make it a little lighter weight, and then go through that FEA process again. And then back to design, and I'm getting exhausted just talking about it, let alone the time that's involved in actually doing it. And you can see here, they came up with a standard looking part, aviation part. If you ever look at aircraft parts, they all look very similar to this, have kind of like this ribbed structure in here, holes poked in, pockets poked in to reduce weight. And this conventional design process ended up with a part that had a mass of 9.15 kilograms. And an incredibly long 3 months to design this one part. Using an optimization or simulation-driven design process where the simulation becomes part of the initial design. Not only were we able to create a part that had a substantial reduction in mass, was that 1.6 kilogram, 1.4 kilogram, 2.4 kilogram reduction there. But we've been able to reduce the design time to a mere 3 weeks. 25% of the original design time, 75% reduction in design time. So we achieved two incredible goals: a reduction in mass and a tremendous reduction in design time. And that's because we don't have this massive iterative process where you're just kind of guessing at things and then running the analysis and then re-guessing. You're letting the analysis help you understand at the beginning the best design. And you can see this is a really impressive design. Lots of areas that have been taken out, streamlined many of the load paths through here, and we end up with a much better design. Another example here where there was a 23% weight savings, but we were able to include manufacturing, or in this case, casting constraints to make sure that it was manufacturable. And then last but not least, this bracket right here, this is my favorite just because it really shows the capabilities of Inspire, where almost at the last minute, they decided they wanted to re-engineer this antenna mount bracket. This is used on a satellite, and it is to hold an antenna in proper orientation. And this looks exactly like, if you ever look at any of the designs of the Mars Pathfinder robots or satellites, they tend to be boxy with little rivets all over it. Well, they decided, again, almost at the last minute, that they wanted to redesign this thing. They wanted to take weight out of it, because when you're putting things into space, weight is everything. The more mass you can take out of it, the less propellant you need, the cheaper it is, or the more cargo, the more payload you can put up there. So they were able to achieve a 42% weight reduction. And I like this because they actually just took and 3D printed the design. They didn't re-engineer this in any way. They just 3D printed the design, probably out of titanium. And the most important part is, when we're doing this sort of optimization, we've got conflicting goals here. We're looking to remove material to make the part as light as possible. But the act of removing material will reduce the ability for that part to resist stress. It will reduce the stiffness of the part. So we've got conflicting goals here. So it absolutely requires us to intelligently remove material to make sure that we achieve the goals we're looking for. And that's especially important when you're putting something into orbit, because there's no going back for it. Once it's up there, that's it. And if it did not survive the stresses of the launch, you just threw away millions or billions of dollars. And in this case, the final design was validated for static behavior, strength, and stiffness, and all of the design criteria was satisfied. This is a little bit of an old slide because this is the first prototypes are printed and be tested for qualification. It has been tested, it did qualify, and it is currently orbiting the Earth, holding that antenna in the exact orientation that it needs to be. That's the power of Inspire. That's the power of simulation-driven design. And that's it for slides. I will not bore you with slides anymore. Everything else we do here is going to be live using and utilizing the software. I would ask you, if at any point in time you have any questions, please do not hesitate to post them into the question and answer, the Q&A box there. I've got it open, and I'm going to be monitoring that through the entire presentation. So if you have any questions, please don't hesitate to ask them there, and I'll address them as they come up. Beyond that, we will have a 30-minute kind of general Q&A session at the end of this. Okay, so I've got my part here, and this part, as I mentioned, actually I will bring my slides back here for just a second. This part mounts on the door frame right here and right here. I'm sorry, on the frame of the aircraft right here, and mounts on the door. And that little nose right there slides into these slots on the door and on the aircraft frame. And that's what holds that hinge in place. So we're going to have two of them that are oriented kind of like this on the frame of the aircraft, and two of them that are oriented like this on the door of the aircraft, and that hinge is going to go in between them. And this is the currently designed part. We can come over here and click this little button here. This is calculate, and it will tell us the part currently weighs in at 4.2656 kilograms. We probably can give that a little bit of a weight reduction by finding out what material this is made out of. And you can see if I click on it down here in the property editor, it will show us the part is currently made out of steel, AISI 304. That was automatically assigned when I brought that geometry in. And in regards to bringing geometry into Inspire, we simply need to come to File, Open, and it will show us everything in our directory and all of, whoa, that wasn't good. Okay. Don't know what just happened there, but we'll bring that back. So I'm going to come here to File, Open. Shows us all the files in the directory. All of the different CAD formats that we support are listed here. So all of the popular CAD packages, CATIA, Paris or Pro-E, SolidWorks, UG, NX, as well as kind of the intermediate formats, the Parasolid, the STEP, and IGES. We support them all. We just need to open them up, and it will open up. I think I just clicked the wrong. Yes, I did click the wrong thing. We'll grab this one here. There we go. It will open them up here in Inspire, bring them in the format that they're the orientation, and in the organization that you had in your CAD model. So you see, I only have one part here. We'll talk about multiple parts in a little bit, but whatever or however you had your part organized in your model in different parts, different layers, whatever, that will be maintained in Inspire. And it will automatically assign it to steel material. I want to change that though. This isn't going to be made out of steel. This is an aircraft part, which means it's going to be made out of aluminum. And in particular, it's going to be aluminum 7075 T6. So all I need to do is right click on my part, come to material, and you will see a list of all of the materials we have in our database here. So steel, down through plastic nylon. That is included in a material library in the software. And I'll select that 7075 T6 aluminum there. And as soon as I do that, you see we've given a tremendous weight savings. We brought it down from 4.2 to 1.5 kilograms, which of course is why aluminum is the favored material in aerospace. But if you have a situation, and you more than likely will, where you've got a material that you're looking to make your design out of that isn't in this library, it's as simple as coming over here to the structure ribbon. You see the ribbons across the top are where we've broken the software up into different categories of functions. Structure, we were in geometry, which is all geometry tools for editing and creating geometry. Moving over to structure is where we have the tools for the structural setup of our analysis. And in here we have materials. So I can come to materials and you'll see the material library. So this is the information of all the materials that are already in the library. And then if I come to my materials, I have all of these here. So let me get rid of these here. All I need to do is click the plus. We'll create a new material. I can click on that and rename that to whatever I want. We'll call it Eric's material. And then I just need to add the material specifications. In particular, it's looking for the Young's modulus, the Poisson's ratio, the mass density, the yield stress, and if you're looking to use heat as a load, the coefficient of thermal expansion. And it's asking for it in terms of megapascals. The reason why it's asking for megapascals is because I am currently in the millimeter Newton kilogram second unit scheme down here in the bottom corner. If I change that to any of our other unit systems, so say inch pounds force, you see now it automatically updates all of those material specifications to be in terms of pounds force per square inch. And density is in terms of pounds per foot. Oh, wait a second. Sorry, I picked the wrong one. IPS. There we go. Yeah, there we go. Now it's in terms of square inch. I had it apparently in terms of foot. So we can change our unit setup, unit scheme, anytime we want during the setup, and it will not have any adverse effect on our model at all. Everything in the model will automatically update to the new unit setup, and it will be the exact same model that you have, just with the new unit scheme. And so you add those in, and as soon as I do that, when I right-click here, that material will now be part of the material library. But again, I have it in what I want it to be in. So with this setup and the material defined, I need to now define the parameters for the actual analysis. So what we're going to do is, somebody else designed this part. I don't know who it is. I don't know what criteria they designed it to. So I want to get some sort of baseline understanding of the setup of this part. I want to understand what sort of stresses, what sort of deformations the currently designed part is experiencing, so that when I now get around to coming up with a new design, when I redesign my part here, using optimization, I'm going to make sure that it is better. So to understand the current design, I need to do an analysis on it. Fortunately, that's incredibly simple within Inspire. From bringing in the geometry, I literally could have this running an analysis in 4 to 5 minutes. It's that easy to do. So the first thing that we need to do is define some sort of constraint system on here. And if we come up to stay in my structure ribbon here and come to loads, this icon right here, and Inspire utilizes what we call multi-function icons. Multi-function icons mean that many of our functional icons actually will bring you to multiple functions. So for instance, if I come to the loads icon here, I can select these little cones down at the bottom, which are our supports, a force, a pressure, a torque, come over here to my load cases. So each one of these different functions, each one of these different tools is accessible from the same icon. And what I can do is come over here, and if I hover over these supports, it's going to say apply supports to hold a part so it doesn't displace when loads are applied. You can apply supports to a point, edge, face, or hole center. So a little tool tip, a little help is going to pop up there, but essentially this is how I hold my part in place, and it has to be held in place for a linear static analysis. It can deform. In fact, we expect it to deform, but it has to be rigidly held in place so that it does not displace. It cannot move. It can only deform. And I do that through support. So if I come here to my support, it now says select a point, edge, face, or hole, and you can see I can do an edge, a point, or a face, or a hole. If I select a face, it's going to put a little cone on there. That cone is going to appear wherever I selected. But the fact that that entire face turns red when I have that cone highlighted means that that entire face is now going to be rigidly constrained. If I need to allow it to move in a certain direction, I need only double click on it and then select any one of these arrows. And as soon as it turns green by clicking it, you can see my icon now has these little roller wheels on here, indicating that it can now translate in that direction, which in this case is the X axis. So it will be locked in the Y, it will be locked in the Z, but it will be allowed to translate in the X axis. So we can create more complex constraint schemes this way. If I don't want it to be in the exact X-axis, I simply need to come here and come to this move icon or move support. And now I can orient that in any direction that I want. It's going in 5-degree increments as I rotate, but I can type in any increment that I want. And now it's free to move in that direction. If I select another arrow, it will now free it up to move. So let me delete that, because what I'm actually going to constrain are these bolt holes down here at the bottom. So I'm going to come here. And if I select these now, it's going to put a slightly different looking icon in there. And with this icon, it is recognizing the unique feature of the fact that I put it into a cylindrical hole. And it realizes that if I'm constraining a hole, it's more than likely because I'm either pinning that hole in place or bolting it in place. So the freedoms that I now have, if I double click, are the ability to free up rotation about the axis using that, or translation about the axis, along the axis using that. But it will always remain constrained normal to the axis. So I can get some complex and realistic constraining schemes going here. So now my part is held in place. It's not going to move. The next thing I need to do is define some sort of force or input onto this. And to do that, I just need to come up back to my loads icon, and I'm going to come to this little force that says apply a force to a point, edge, face, or hole. You can create a distributed bearing or traction force as well. So just like with the constraint, if I hover over a surface, a line, a point, or a hole, I can put a force on that. So for instance, if I now put a force on this upper surface, again, the icon doesn't matter where that icon is placed. It's going to apply that force to the entire surface. and then I can put in the value for the force. So if I say 100 pounds force, that will be applied to the entire surface. And in fact, if I hover over it, you will see that it now says that the force one is 100 pounds force, but the equivalent pressure is 9.0868 pounds force per square inch. So it is calculated how to distribute that force across that entire surface. And it would distribute it across a line or a hole as well. Obviously, if I select a point, it will apply all that force directly on that point. But that's going to be going in the center of the hole here. So I can come here to the hole, click on that. It now will distribute that force evenly across the entire hole. And again, I just need to put in the value of my force here and select the orientation. In this case, it happens to be oriented in the correct direction, which is in the negative Y axis. So if I have my part like this, it's going to be pulling down like this. And this is going to represent a scenario when the door is open and the weight of the door is pulling down on this bracket. And the magnitude of that force, I will make 500 pounds force. But say, for instance, it wasn't perfectly aligned up with the y-axis. I needed this to be some sort of other direction. And I have the ability to say the x, the y, the z-axis, and plus or minus in any of those just by clicking buttons here on the micro dialog box. But if I need this oriented in another way, I can change its orientation similar to the way that I did it with the constraint by selecting the move force. I again get these little manipulators here, and using these, I can, and then in this direction here. And again, it will do it in 5-degree increments, but I can type in whatever I want. So say I wanted 43.8, it will orient it that way. If you don't know the angles of your force, but you instead know the components of a direction vector, I need only come here and open up this little slider right here. And now I can put in the components of my direction. See, right now it's pure negative y, so it's negative 1y. By default, this is a unit vector. So it will make everything, if the equivalent was combined, you would end up with a 1. And in fact, if I come here and orient this slightly differently, you see now I'm seeing the coordinates of that unit vector. I can put in whatever I want here. I don't have to simplify it down to a unit vector. I could come in and say 3, 4, 5, and have it orient that way as well. This did not affect the magnitude of the force. The magnitude of the force is independent from this manipulation. This is simply the direction of the force. If I need or have components of direction and magnitude, so true vector components, I just come over here and I click this little icon, which is my component force mode or direction force mode. So right now it's direction force mode, which means that those values only affect the direction. If I change it to component force, now these values affect the magnitude as well. So I'm seeing the actual vector components of magnitude and direction. It calculated them automatically for me. But if I change this to, say, 100, not only has the orientation, the direction changed, the magnitude of the force has changed as well. And if I change this, it keeps the same orientation that I had, but adjusts the components to make sure that it is oriented the same way, but now has the new magnitude. So whether you know that it's pointed in one of the cardinal axes, excuse me, you know the angles off of the cardinal axes that you can orient it to, you know the overall magnitude and then the components of the direction vector, or you just know the magnitude components of the vector. However, you know the orientation and size of your load, we can put it in this panel here. And now, of course, as I mentioned, with 500 pounds force. And again, if any of you have any questions whatsoever, please do not hesitate to post them into the Q&A. I will address them as they come up. I want to make sure that you get the most out of this, so that excuse me, so that if you have questions, addressed as it's fresh in your mind. And also, I can pretty much guarantee you, if you've got a question, there's a good possibility that other people are thinking the same thing. So please don't hesitate to ask. You'll help yourself and help others as well. Okay, so I've got that one force in here, that door hinge bracket, and there are two main states for the door. Either the door is open, and as we saw, it's hanging here along the side of the vehicle, or the door is closed, and the closing mechanisms are providing tension on that door, holding it in place. And thus that tension is going to be relayed back to the frame and to the door. So I have another situation when the door is closed and it's being tensioned and held in place. So I'm going to come here, activate my force again, and click on the inside of the circle and get another force. Now I have a second arrow here. And if I look over in my browser, I've got force 1 and force 2. If you are looking to add many, many forces to your model, and that's great, you can also come here and rename this. So I could come here and rename this force to door open, and then rename this force. And you see, as I hover over it, it does highlight it in the window here. And if I hover over here, it does highlight it in here as well. So we kind of do that bi-directional communication, so we can very easily identify what is what, and I'll call this one door closed. The advantage to this is if you've got into load cases, which we'll be doing shortly, is going to be much easier if we have them intelligently named. So now I have the door closed. This is not going in the right direction. This, I need to go into the z-axis, the positive z-axis. So now that's oriented properly. And then I need to give it a magnitude. Now, if I type a value in there, so if I type 350, that's going to be registered as 350 pounds of force. Why? Again, because we are currently in the inch pounds for seconds unit scheme. But say I knew my force in terms of newtons. I could go and use my calculator and look up the conversion in between the two and do a conversion and type that in, or I could Google it and say, hey, Google, what is 350 pounds or 500 pounds of force in, I'm sorry, 2,000 newtons of force in pounds, and put it in that way. Or I could just come here and type in 2,000. Now we know if I hit enter, it's going to make it 2,000 pounds force, which is completely wrong. But if instead of hitting enter, I type in N, so the abbreviation, of course, for newtons, as long as it's one of the supported units that we have in Inspire here, and you can see all of them, as long as it's one of the supported units, it will automatically convert it into what unit it's expecting it to be in based upon my current unit scheme. So I didn't have to do any conversion. I just typed in 2,000 newtons and it came back 449.61788 pounds force. I know that's something that we could do on our own, but I think this is a really cool feature that that's going to save you a little bit of time. And you're going to find all throughout Inspire, you're going to find a whole bunch of these little features that are going to save you a little bit of time here and there. So now I have my two forces on here. I have them pointed in the directions that they need to be. I've assigned them their magnitudes. But as it is right now, these forces will act at the same time. And I don't want that. There's no way that the door can be open and closed at the same time. And I need answers for both of these scenarios, but they're not going to act together. Equivalent force, which is going to come off probably at a 45 here because they're close to the same thing. But that can't happen. We have this this function, this tool within linear static analysis that's called the load case. And a load case, quite simply, is a combination of a force or multiple forces with a support or multiple supports that are going to define some sort of loading scenario. And that's exactly what we have here. We have two loading scenarios. Both of them are going to use all of the constraints, the bolts that are holding it to the frame or the door. And then we're going to use each one of the individual loads in its own separate load case. And that means that once I click go, once I click run on this, it will analyze both load cases as independent processes. It will not have them act together, and I will get two answers, one for the door open and one for the door closed, which is exactly what I'm looking for. So if I come here to load cases, and I add another load case to this, and just like I could with the loads, I can rename this. So I'll rename this one, and I'll call it door closed. And then I just pick kind of buffet style what supports and what loads I want. So I come here and say, okay, I want to use all of these supports. And then since this is door closed, I want the door closed, but I don't want door closed in here. And now I've defined two independent scenarios. So you need to figure out all of the different loading situations that your part or your assembly or your vehicle or whatever are going to experience. And then you put in all the loads and then you just piece them together in these nifty little load cases. Which means that coming up with a new scenario is simple. I just click plus. So we're going to call this one closed broken bolts. So closed broken bolts isn't showing up entirely on there. But what we're going to do is we're going to use the door closed. So we're going to assume the door is closed, but we're going to imagine that two of these bolts have failed. They've broken, and we want to see what happens. So and you can see by selectively picking things, I've now gone and made it so I've got a brand new scenario that I didn't have to define. And I could go through and continue to add these, put in new forces, put in new anything, and create load case after load case after load case. That's going to mean I only have to run this model once, and I'm going to get all the answers I'm looking for. And more importantly, when I get around to the optimization, it will take and it will optimize for each one of these different scenarios. And that's it. I could do things like enforce displacements, G loading, angular velocities, accelerations, temperature loads, masses hung off of it. But for what the analysis I'm looking to do right now, this is exactly what I need. And so I'm going to now come over here. I'm going to come to my analysis button. And now I can run the analysis. Now I know that this has gone, we've been going over this for what, a good 30 minutes or so. And that was to make sure that I explained absolutely everything I did and all of the different aspects of each one of the different functions. But I think you could recognize that had I not been talking through this entire thing and just loaded up the geometry and did all of my work, I literally could have had this running in 3 to 4 minutes. That's the power of Inspire. How quickly and how easily you can prepare analyses and get them running. Now I can also, and I can name my analysis, and that's useful if you're going to be running multiple iterations and multiple scenarios. Name it, because that way every analysis that you've done is saved within the model, and it allows you to go back and view your past iterations, your past analyses. I'll just leave it called exercise 2. It's just grabbing that from the name of the model file. If I want to incorporate a normal modes analysis, so I want to know how the part is going to vibrate, I can do that and ask for a certain number of normal modes. The default is 10. We'll leave it at that. I can do a buckling modes analysis. Speed versus accuracy, leave it on more accurate. If you know anything about finite element analysis, this is a second order tetrahedral element, whereas speed is a first order, but please leave it on there for the accurate results. And then contacts, we'll talk about more about those in a second or in a minute, but now I just click run. And what will happen is it will take this part, and where Inspire really excels is the fact that it's going to utilize our tried and true enterprise level softwares as the backbone of this. Once I clicked run, it began meshing it using our tetrahedral batch mesher to guarantee the highest quality mesh available or possible. Then once it's done with the mesh, it's going to send that to Hypermesh, our preprocessor, to get everything ready, all the element definitions, the material definitions, assign the loads that were just that were put in, and prepare everything for the analysis. And then finally, it will send it to OptiStruct, our analysis code, to actually run the analysis. And when it's all done, it'll come back here. And now I can view the results. But before we do that, let me just open it up for any questions that anybody might have. Okay, well,
no questions in the Q&A.
Excellent, thank you. Okay, so let's take a look at the results. And this is what we have here. It defaults to showing me the displacement results, so it will show me what the deformation is due to those loads that I applied there. And I have each one of my different load cases that I can look at. So door open, door closed, and closed broken bolts, as well as my normal modes. So in my door open, I can see here that my maximum deformation is 2.166 e to the negative 3 inches. So a little bit over 2 1,000ths of an inch. So very, very small deformation, which is great. I don't want this deforming much. If I want to see the animation of that deformation, I can click the little play button here and we'll get that. Now, you're looking at this, I would sure, and saying, whoa, that looks like a whole heck of a lot more than 2 1,000ths of an inch. Which in this case it is. And that's because most of the time when we run linear static analyses, the actual deformation is microscopic. In fact, I could show you what that looks like shortly. So what people normally do when they run an analysis and they look at the results is they scale it up so they can kind of just see the general behavior. How is the part deforming? I know that this is not the real deformation, but I need to understand how it's deforming. The only way I can do that is to scale it up. So Inspire does that automatically for you. If you need to check that, I can come down to this icon right here, the displacement scale factor. You can see it scaled it up 345 times. And now I can come here and make that 1, and we can see that. I see there's a question in there. I'll get to that in just a second. And now I can come here. So Brandy, yeah, if you could read that question to me, that would be great.
Sure thing. So the question is, does it require us to have any other software for the simulation?
Ah, fantastic question. I'm glad you asked that. No, it does not. Inspire is a fully enclosed package. So I mentioned that it's going to go and it's going to utilize all of our other packages in the background, but you don't have to have those installed. All of the libraries and everything that's necessary for Inspire to do everything that it does is all included in the one download. And as we get to the end of this, I will go and show you how to get your hands on that software, because you can get it for free, either for a student edition, or we do sponsor teams as well. But you're going to download one package. It's sizable. It's like 1.5 gig is the download for Inspire, and I think it comes out to somewhere around 1.75 to 2 gig for the actual install. But that's everything. It's an all-in-one package. All of the executables that are handling in the background, all the libraries, all the analysis is included in here. So you do not need anything else. So great question. I appreciate the question. Now I did change this to a one-time scale, so you can see, to really see the actual deformation, I had to really zoom in, which is why we automatically default to scaling it up. But we can see that. Now I can come here and I can also change this to door closed, and I can see the behavior of this with the motion that or the loading for the door closed. And then I can also view the broken bolt one. So you'll see it is now, those bolts are broken, and it is shifting up as a result of that. So I've got all three analyses ran together, but their results are all separate. That's the displacement. But what I'm mostly concerned about is the von Mises stress. And so the default for von Mises stress is going to look something like this. It's going to use what we call a divergent coloring scheme, which is red, white, and blue. Blue meaning it's below yield, white meaning it's at yield, and red meaning it's above yield or thereabouts. And you can see my part here is nowhere near failing. Yeah, we've got a few spikes here on this 90-degree corner, and we've got a few spikes here on this 90-degree corner going around the bolt holes, but those are nothing that we need to be concerned about. And in fact, if I come here to my other option and change to % of yield, my entire part is essentially at 0% of yield, or if I come to factor of safety, my entire part has a well over 6 times factor of safety. That's great. The part is very, very safe. But there's a problem with that as well. It is way, way over designed. This part at 3.29 pounds or 1.5 kilograms doesn't seem like it weighs a lot, but if you imagine that for each of these, for every door, I have 2 of these on the frame of the aircraft, 2 of them on the door. That's 4 of these for every door in the aircraft. And I can't remember offhand how many doors the A380 has, but it's a whole bunch of them. And so at 3 1/3 pounds, that's 12, 13 pounds of door hinge bracket per door. We'll assume, 8 doors. I don't know exactly how many, but we'll assume 8 doors. So that's what, 100 pounds of door hinge bracket on every A380. So that's a sizable amount of mass, a sizable amount of weight. And then we take and think about the fact that there are many, many other parts on the aircraft that perhaps are as over-designed. That's wonderful to have a part that has a 6 times factor of safety, but you don't need that. And it means we're lugging around far more aluminum than we need to. And aluminum doesn't pay to fly. So we want this part to be as light as possible. We want it to be safe. We want it to meet structural criteria, but we want it to be as light as possible. And that's where analysis or optimization is going to come into play. So what we're going to do now is talk about optimization and how to take our well-designed part and make it an even better design by going through and running it through optimization. And I just noticed here, so there's another question. It doesn't matter if a small segment of the part has a low factor of safety. Yeah, another excellent question. So if I come back here to factor of safety, you see that the factor of safety is more so a kind of a blending of everything. So you're not even going to see those occur in here. Where you're going to see those localized areas are when I come here and I look at my von Mises stress, or perhaps at my percent of yield. If I see very, very, very localized results. So this right here is probably, in fact, if I come here and put my elements on, that's not even stretching across an entire element. That is what we call either a point force or a stress, or a point stress or a stress riser. That's as a result of the geometry and the limitations that we have as a result of the types of elements that we're using. If you see something like this, that's simply because it's resisting movement in that one area, and it's not realistic. They tend to happen around sharp corners, and they tend to happen in the immediate area surrounding forces. This right here, yes, it's a little bit higher, and let me stop this. It's a little bit higher in this because this is a 90-degree curve, but also remember that for the most part, we're not going to have sharp 90-degree edges on our parts. A simple fillet on that is going to make that go away. So as long as your stresses are very, very localized, they typically don't see them as issues. And when you come to your final design, which will have fillets and everything on there, you'll probably get a much more realistic view of your actual stresses. So hopefully that answered that. So great questions, keep them coming. Okay, so I do want to talk about optimization, and we'll do that shortly here. But before we tackle optimization, what I want to do is talk about scenarios where you have multiple parts. Right now, this was just one single part. But in many, if not most cases, you're going to have an assembly of parts working together. And how do we deal with situations like that? So I'm going to come here. I'm going to open up another model I have here. This probably should look a little familiar. I'm sure you've all seen quadcopters, these drones here. This is just a rough body for a quadcopter. You can see it's got 4 legs coming out here. It's got the mounting points for the propellers, for the motors that are going to drive the propellers. And it's made up of these three segments, which make up these individual legs. It has a top plate and a bottom plate that these legs are wedged between. And someone's even come along and modeled in the geometry for all of the bolts and screws that are holding this together. So I've got probably a couple of dozen different parts here. And I have not said anything about how these parts are going to be connected to each other. That's another one of the great features of Inspire is you don't have to worry about that. If I do nothing else and I just constrain this and load it, it will act as one whole body. So if I come here and, we'll just say, okay, constrain on the bottom of the feet here, grab these, and then I'll come here and I'll just draw. So if I put a force onto this, so if I put a force here, it's going to apply it across the entire thing. I don't want that. I want it in a localized area. So if I need a force in a localized area, I can just come here to geometry. I'll just draw a circle on here. We'll sketch on this, and I'll take and draw that circle. We'll make it a 2-inch circle. And then right click to get out of here. Now, if I come to my force, I can put it just on that circle, and we'll put a 50-pound force on that. And I'll come here, and I'm going to highlight everything. And now I can come here and change this. We'll make this out of. We'll pretend we 3D printed it. We'll make it out of ABS plastic. Okay, so now if I come here and I run this, I didn't tell anything. I didn't tell it how to deal with the multiple dozens of parts on this. I didn't say connect anything to anything else. But yet what you're going to see when this gets done, and hopefully it'll get done real quickly here, what you're going to see is this is going to act as one unified part. I don't need to do anything else to this, and it will all be connected together. And the reason for that is because by default, Inspire creates contacts. Anytime you have multiple parts coming together, when those two solids touch each other, it will create a contact between them. We call it a bonded contact. That means that they are stuck together. And it will act as one single part. So this, even though it's all of these multiple dozens of parts, is all contacted together. And that's great. That means I don't have to worry about anything. But if I do want to worry about things, I could realize that this perhaps is not, well, it will work perfectly fine and I'll get reasonably good answers. This is not an exact representation of reality. The representation, the reality is this part right here is going to be wedged between these two things here. And with the bolt going down and bolting on the bottom down here, the bolt is actually what's going to carry the force, carry the stress through the entirety of the part. Not the fact that it is assuming that it has been essentially crazy glued at the top and the bottom. So this isn't an exact representation. It will work, and that's what we want it to do. But if I want it to be more realistic, I can get there without a lot of extra work. And to get to that point, the first thing I need to do is come here and delete all of my bolts. I could come and delete them manually. I could highlight it and click the delete key. But I don't want to do that manually. All I have to do is come down here, select one. I'm going to do a shift select and delete that. I'm going to leave these spacers here. So I'm going to come and grab these here and shift select and grab those. And now they're gone. Interestingly enough, because of these bondings, the part will act exactly the same. So what I can do now is come to this fasteners option here. Fasteners is going to look for situations where I have multiple parts with holes running through them. And if it's a hole that goes all the way through, it's going to put a bolt. If it's a hole that only goes partially through, it's going to put a screw. And I can get now an FE representation of those bolts and screws. But most importantly, what's going to happen now is it automatically changes any contact that was affected by the addition of that bolt or screw is now going to be changed from bonded to contacting. What that means is this is no longer super glued to the top. It will not pass through, but it can slide across it. So it's a much more realistic. And in fact, if I truly want a very accurate representation of it, when I come to my run, these contacts sliding only mean that this, imagine taking two real strong neodymium magnets, putting a layer of oil between them, and putting them together. I could slide them across each other, but I couldn't pull them apart. Sliding with separation will allow these faces to separate from each other if it determines that the forces on the part would dictate that. And I get a very, very accurate representation. Now, you don't get anything for free. First of all, it did take me doing a little bit of work, not much, but a little bit of work here. And second of all, sliding with separation will add a little bit of time to the analysis. Again, not a tremendous amount. But you do it this way, you click the run, go grab yourself a coffee or take a lunch break, or, you know, if it's a real complex model, click it before you go to bed at night. And you'll get much more accurate results. So I was hoping that this analysis would be done, by the time that, but it's going to run for a while. So we'll take a look at it in a little bit. But I want to move on to onto optimization. So the remaining 15, 18 minutes we have here before we go into question and answer, though we have been having some good questions up till now, is going to deal with doing, and we may run a little bit longer than 18 minutes, but that's fine, is going to deal with setting up an optimization. So let me bring my exercise 2B back. Now in optimization, you saw that that bracket, this right here, where it kind of created these members here, and more so this guy right here, where you've got it kind of got these little structural members coming across here. These were created through a concept called topological optimization. And topological optimization is a lot like carving a sculpture. If you want to carve a sculpture, you take a block of material, you get rid of all the material you don't need, and reveal the sculpture that was inside that block of material. If I want the best, most optimized, lightest part possible, I'm going to take a chunk of material and determine what of that chunk of material is necessary. And to do that, I need a good chunk of material. Because the solver is going to analyze where the load is and how the load passes through the part to the constraints, and to make sure it's got material there. But with my currently designed part, if it wants to get the load from here to this back thing, it can't. Because this part has been designed and because they put some lightweighting features in it already, there's no material to go through. So by taking and optimizing my currently designed part, it's almost exactly like trying to take and carve a statue from a statute that already exists. And that's not something you're going to do because it limits your ability. So what I want to do is I want to give it a nice big block of material. And so I'm going to take and get rid of all of these lightweighting features on here. This is something you could do in your CAD package if you wanted to. If you're a CAD expert, you got a CAD package that you're a master at, do it in there. But we have some nifty geometry tools within Inspire that are going to allow you to do it pretty easily too. So I come here to my geometry ribbon and I come to simplify. First thing I'm going to do is get rid of these little pockets. So I'm going to come to fill holes. It recognizes some holes, but not all of them. To grab these, all I need to do is double click at the bottom of that. Click one more time and it's going to fill that in. You see what I'm doing here is I'm filling these in. I don't want those features in here. I want Inspire to determine how to lightweight the part. I don't want to direct it in any way. Now, another thing somebody's done is they've gone and they've carved these angles on here. I don't want those. So I'm going to come here. I'm going to grab this and slide that on out. My push-pull allows me to grab a surface and push it or pull it. And if I pull it all the way to the point that it reaches where those two come together in a 90-degree angle, it just pulls it to there. So I can get rid of these all the way to there. And now this is a nice block of material to optimize from. So the solver will come along and it will determine what of this material is necessary and get rid of all the rest. But there's a problem in that. And the problem lies into the fact that there are parts, aspects of this design that I can't have it carve away. To be able to attach to my door hinge, there's going to be a pin or a bolt or something put through there, probably a clipped pin. And that means for this to work perfectly, I need to have this as a perfect cylinder. I can't lose that cylinder, which I would be at risk of if it's carving away the material for an optimization. So in this case, what we do is we partition our areas that can't be removed, what we call our non-design space. We partition them out. I come here and now I just specify how thick I want that partition to be. And it will create a separate solid. Then I'd come and do the same thing to these bolt holes here, but in the interest of time, I won't waste your time with that. I just right click now and say design space. Now this big red area is what will be carved away from. And any of these gray areas will remain. Now let me cheat here a little bit. I'm going to open up exercise 6A here, which is this part already partitioned out with the loads put back on it. And now like I said, I just right click on this select design space. So anything you see in gray is going to stay. It will not touch those. It will use them as part of the analysis, but will not optimize them away. It will not carve that material away. Anything in red, free game. But to get rid of material, I need to tell it how to do that. And that requires me coming back here to structure and defining my optimization. There are two main things we need for an optimization from the setup standpoint. We needed a whole bunch of things from the actual modeling standpoint: design spaces, non-design spaces, loads, materials, all that sort of stuff. But to set up an optimization, there's two main things we need. The first of which is what we call an objective. What's your goal here? What are you looking to do? So is this similar software like Autodesk using generative design? Yeah, so what had happened was we have been doing topological optimization for decades now. For about 30 years, we've been mastering the concept of topological optimization. Autodesk, there's another one out there that does a generative design. They realized that there's an opportunity to do this as well. So they copied our topological optimization concepts. There was not so much copy in that. They decided to start utilizing them. Topological optimization is a well-defined mathematical process. So they decided to start incorporating it in as well. And they came up with this nifty new name, Generative Design. It's still topological optimization at its core. I know their way of doing it has some limitations because it's stuck with doing specific things in a specific way. It's nifty, and it can give you some cool designs. It's definitely not topological optimization. It's not the power of topological optimization. And I think you're going to find that this is going to give you better designs and it's going to be easier to do. So yeah, it's similar to it. You're going to get designs that look similar. But if you really want a good mathematically based design based upon these, based upon the stress, based upon the stiffness, you really want to go with topological optimization. That's the true way of going about doing things. Generative design, it's nifty. It's similar. I mean, we could call ours generative design too if we wanted to, but they had to come up with some new name for it. So it's all right, but you really want the power of topological optimization if you want a good, reliable part. Okay, so answer that one. Good deal. Okay, so now we've got this defined. My objective here is to maximize stiffness. The objective is what we're looking to achieve. And maximize stiffness is going to give you a part that maximizes the overall stiffness of the part. It's going to look to make sure that the material is distributed to get the maximum stiffness. Now, left to its own, it would keep all of the red part because that is the stiffest part possible. So I need to provide it some sort of limitation. That's the other requirement. And in this case, it's a mass target. So the result here says you cannot use more than 30% of this big red block here to give us the maximum stiffness. So 70% of this big red block is going to go away. Your other option here, minimize mass, what this is going to do is it's going to try to make the part as light as possible. So I'm not going to pre-describe how much I want taken away. I'm going to say, minimize the mass of this as much as possible. And again, left to its own design, it would now get rid of all the material. So I need to provide it some sort of limitation. And now this one is a stress constraint. So I say I want a safety factor of 1.5. It's going to take the yield strength of the material. It's going to divide it by 1.5. And it's going to set that as a limiting stress factor. So as material begins to get carved away from this, and the stress begins to rise, it's going to make sure that that stress does not go more than the yield stress divided by 1.5. And then I would run the optimization. This would take probably about 7 to 10 minutes. So we'll cheat here again, and I'll bring you the results and we'll take a look at the results. And this is what we would get from a topological optimization. And I can play with that design. I can add a little bit more to it, take a little bit away from it. But this is the topologically optimized design. To make sure that you have the best material utilization to get the lightest, strongest part possible, this is the shape, or this is the orientation of material that you'd want to do. Now from here, I can click Analyze, and what it's going to do is it's going to run a quick analysis on this just to make sure that we've achieved all of our goals. So we can see the stress on there, we can see the safety factor. And that shouldn't take too long. Additionally, from here, I can click this Fit Polynerbs, which is going to take and it's going to fill this with a geometry, a nice smooth geometry. So now I could take this part and I could bring it into my CAD system. and design from there. Am I just going to 3D print this part? Probably not. I'm going to engineer it into a nicer looking part, then a little bit cleaner looking. But I could, with this geometry, I could bring it into my CAD system and go from there. So now I've got the end results of my stress analysis. So I'm going to come here to my factor of safety. You can see I've got not as high of a factor of safety. In fact, if I trim this down, you see I still have some, but as I get down to 1.5, which was my cutoff, everything is gone. So I have a minimum of a 1.5 on my entire part. And again, most of my stress is going to be concentrated in these sharp corners, which I'm going to put a fillet on anyway. I just wanted to leave them as it was to allow the optimization code to have the best chance of getting a good design, and then I will engineer it from there. And I can't stress enough, no matter what company you're hearing from, because a lot of these generative design companies will say, well, just let us design your part for you. You're an engineer. You're going to school to be an engineer. If software could design parts for you, then you wouldn't need to learn to be an engineer. Software is a tool. Software is going to help you understand how to design your parts better, but at the end of the day, it's up to you to design it. You take information from this and you design your parts from that. So this is what we can see as an optimum design. And I can take this into my CAD system and come up with a good design from that. Now, where do we go from here? That's still plodding along. Where's my, oh, there it is. If you want to get the software, a couple of different routes you can take. If you come to altairuniversity.com, you go to students and you select free student edition. You can put in a request for a student edition, a very simple little form to fill out, name, the school, what department you're in, your country, whether you're a student, professor, advisor, researcher, whatever, and then use your school email. Please make sure you use your school email. It's how we verify that you are a student or affiliated with a university, and then you'll get that real quick. It's also going to ask you for the Ethernet host ID. There's some instructions as to how to get that, or there's a little software here that will get that for you. You run this, you download it and run it. It will pop up a little window here somewhere hiding. Oh, it's probably over here. Hold on, there it is. It's going to pop up this, which is going to give you the code that we want. You can copy that and then just paste that into here. It is unique to your computer, so that's why I'm not concerned about giving you mine. It's like a little registration. Oh, thank you, Brandy, for putting that in the link there. It is what ties the license to your computer. So, and then it'll be a year-long license, and you can continue to re-up that for as long as you're a student or a professor or affiliated with the university, as long as you have an EDU email address. The other way that you can go, if you come here also to students, you can come to student competitions. We are a proud supporter of all of the SAE and ASME competitions. So if you belong to a student design team, HPVC team, or any of the other competition teams out there, you can apply for a team license. There are a few limitations to the student version. You don't get all of the software, though Inspire is fully functional. But if you apply for a sponsorship for the team, we will get you as many licenses as you want, and they are full-fledged, full licenses, and then we'll work with you as well. Additionally, once you get sponsorship for a team, you can and thank you for putting that there as well. You can contact me if you're in the U.S. If not, I can point you to the appropriate people in the country that you're in. but we can arrange trainings. I do trainings all the time with teams, right now doing them virtually, just like we're doing this virtually. But when we get back to interacting with people, I can visit your university. We can do trainings with you, do consultations, help you out that way as well. So excellent. And send any request info to us@asme.org. That will get you in touch with me. So that's it for really the demonstration section. There's some more features within Inspire that would be another class altogether. That one's still plodding along, so let me come here. We do have the ability to do motion analysis. Open, note save. If I come to, why is this freezing up? Come on. Okay. Oh, this is frozen up. Darn it. Why did that happen? Well, that's not good. Let me just open something else here. Oh, wait a second. Maybe it just unfroze. Ah, it crashed. Okay. So from India, we want to use it for SAE Baja. Yeah, if you go to that the link that was put into the chat, Altair University sponsorship competitions, fill that out there. That is our global request form, and it will end up in our at our India office. Additionally, if you send an email to as put in there, efes@asme.org, they will contact us, and we can get the appropriate person in touch with you to your email address or to your contact. So for the apply for the sponsorship and then send a request to that efes@asme.org, and we'll get you in touch with the appropriate people. We'd be happy to help you out there. So the other aspect of this that just doesn't seem to be coming up right now, I'll try it again, is, and it's probably because I have this analysis running in the background here. We have the ability to do motion analysis as well, which allows you to simulate dynamic systems and the interaction between different pieces of the system. So for instance, if I come here and let's come to desktop. Oh, there's demo material, demo files, and oh, not there. Motion demo, that's what I'm looking for. Yeah, we'll bring this one up. This one's kind of fun. So this is the landing gear assembly for NA380. And it's running a little bit slow there. It's coming up. It's kind of tough to tell down there. Okay, and so with the motion, what we can do is just got to finish loading the motion results. There we go. I can actually visualize the interaction of this. So by putting motors and actuators on here, we can see how this entire assembly will work and verify that the angles that we've got on our brackets are oriented properly, that we've got appropriately sized actuators and motors on here, that we're going to achieve the clearances that we want. All I did with this was, well, whoever set this up, I didn't create this model, was define the joints between the different parts and set the actuators and time them. And now this is the actual behavior of this properly. Additionally, because it's continually calculating things like forces at joints here, the forces can then be used to do structural analysis and optimization. And in fact, if let me get out of this right here. There we go. If I can find it. I've got motion work. No, not there. Let's see if I can find somewhere in here. I've got maybe it's this one right here. Let's try this. See if this is the right one. Oh, yeah, it keeps crashing because I've got that going on. But I've got a full Baja vehicle that I modeled in motion, and it compresses the suspension, then starts driving forward, hits a bump, and you can actually extract forces and everything from there. And as I think as Darius mentioned, I've got an entire library of videos. If I could find those here, give me just a second. Inspire instructional video series. Where's that at? There it is. If you go to the if you go to YouTube and search for Altair University, I have an entire series of instructional videos that go through all of the structural animation or structural analysis. Here's this one talks about that Baja vehicle that I did. So you can see that right there. So this was all modeled up with springs and suspensions. So there's a lot of information in there as well. Can go a little bit more in depth into this. So just go to YouTube, search for Altair University, and they've got a playlist for the instructional video series. You can go through those as well. So again, that's all that I have. Happy to answer any more questions for the time we have remaining. But in the absence of those, and before we get to the end here, I do appreciate the time, appreciate the great questions, and I'm happy to address any more that that you might have.
Thanks, Eric. That was great.
It's a pleasure.
Do we have any more questions? I don't see any more in the Q&A.
Okay. Well, if any come up, I assume that that the email address you provided, Brandy, is an acceptable one for somebody to send a question to as well for you to forward on to me.
Absolutely. I'll
Okay,
put it
yes.
in the chat again. Yep.
Excellent, excellent. Yeah, so if you have any questions or anything else, run into any problems getting the student version or anything, don't hesitate to drop an email to that. Brandy can pass it on to myself or whoever the appropriate person would be, and we'll get you an answer to help you out. So again, I appreciate your time. Best of luck to all of you. Stay safe, and look forward to working with you and seeing you at eFests in the future. I miss being live at them, but we'll get through this, and hopefully next year we can all get together and have a fantastic eFest in person.
Awesome. Thanks again, Eric.
Thank you.